Okay, so in this video, what I want to do is have a look at another example of a non-homogenous second-order differential equation using Laplace to solve it. So let's have a look at this one. So we've got d2x by dt squared minus 2dx by dt plus 10x equals e to the 2t. So first things first, let's get our definition. So if the Laplace transfer of x equals x bar, the Laplace transform of x dot is going to be s x bar minus x naught, and the Laplace transform of x double dot is going to be s squared x bar minus s x naught minus x1. That's all we need for this. So let's take the Laplace transform of the left and the right hand side. Using the principle of linearity, we're going to be able to separate the variables and then just directly use those substitutions. If that doesn't make any sense, go back to the previous videos because this should be quite intuitive by now. So let's do s squared x bar minus s x naught minus x1 minus 2 s x bar minus x naught plus 10 x bar equals Laplace transform e to the 2t is going to be 1 on s minus 2. And all I've done is just taken the Laplace transform of e to the 2t. Right, we're also told in the question that the initial conditions are such that when t equals 0, x equals 0, and at that point dx by dt is 1. So we can say that x naught is 1 and x1 is going to be equal to 1. So let's substitute that back in over here. So we'll have s squared x bar minus s x naught, x naught is going to be 0, minus x1 is going to be 1. So it's going to be s x bar minus 1, minus 2sx bar minus 0 plus 10x bar equals 1 on s minus 2. Let's just tidy that up a little bit. So we've got s squared x bar minus 1 minus 2sx bar plus 10x bar equals 1 on s minus 2. Okay, x bar, we'll have s squared minus 2s, minus 2s plus 10 minus 1 equals 1 on s minus 2. Now what I'm going to do is take, we'll just move everything up. I'm going to take the 1 to the other side. So I'm going to have x bar, s squared minus 2s plus 10 equals 1 on s minus 2 plus s minus 2 on s minus 2. Yeah? And that's going to equal s minus 2 plus 1, going to be s minus 1 on s minus 2 equals x bar s squared minus 2s plus 10. Yeah? Is this a reducible factor? No, I don't think it is it? So I'm going to divide both sides by this factor. I'm going to be left with x bar equals s minus 1 on s minus 2, s squared minus 2s plus 10. Now, our goal by now is to put this into partial fractions. So that's going to be identical to a on s minus 2 plus, remember this is a non-reducible quadratic factor now, so that's going to be bs plus c on s squared minus 2s plus 10. And now what we're going to do is just find what those factors are. Okay, so now that I've found the coefficients of a, b, and c, a was 1/10, b was minus 1/10, and c is 1, I just plug that back in to our partial equation, partial fractions, and this is what we end up with. So what we're trying to do is find a way to look at what we have and say, I know what the Laplace transform that would cause that image. So we've got something to play with. If we have a look at 1 on s minus 2, well, that's easy. That's just e to the 2t. This thing over here is a little bit more complicated. So what we're going to do is if we take out the 1, and this is where it gets a little bit more just in terms of experience. The more experience one gets with this, the easier you'll know what to do quickly as well. So just to make things more simple. So if we have here, we've got 1/10, we've got 1/10 over here. So we can actually take 1/10 out and just multiply that by 10. So let's do that. So we end up with x bar equals 1/10, 1 on s minus 2, plus minus s, or in fact what I'm going to do, I'm going to change that to minus. So that's going to become s minus 10 on s squared minus 2s plus 10. So if we multiply the minus s by 1/10, we're going to end up with minus 1/10 s. And if we multiply minus 10 by 1/10, we get, sorry, there's a double negative here, so that's going to be positive 1, which is what we have over here. So this is looking a little bit more friendly. But this really doesn't look so friendly at the moment. And we've got a non-reducible quadratic factor here in the denominator. And we don't have an inverse Laplace transform or a forward Laplace transform that we know of that will end up with something like this. So what do we do in this case? Well, what we do, we complete the square in the denominator. So if we just complete the square of s squared minus 2s plus 10, whoops, that's going to go to s squared minus 2s plus 1 minus 1 plus 10, I believe. It's going to go to s squared minus 2s plus 1 plus 9. So what we can now write is x bar equals 1/10 of 1 on s minus 2 minus s minus 10 all on s minus 1 squared plus 3 squared. Yeah? Yeah, you can see that. And you'll see why I wrote the 9 as a 3 squared. So now let's see what we have. S minus 1. It would be really nice to have an s minus 1 on the top, wouldn't it? Why? Because if we have an s minus 1 on the top and an s minus 1 over here, then we can say, well, that looks quite similar to the Laplace transform of a cosine function with a shift, the first shift theorem. So let's just have a look at that. And you'll see what I mean. So we have x bar equals 1/10, 1 on s minus 2, so that's the easy bit, minus s minus 1, s minus 1, and to get to minus 10, we'll have minus 9. So let's change the 9 to the 3 squared, all on s minus 1 squared plus 3 squared. Yeah. Now we can separate those, so we can say x bar equals 1/10, 1 on s minus 2, minus s minus 1, all on s minus 1 squared plus 3 squared. The double minus is going to be a plus, isn't it? Plus 3 squared on s minus 1 squared plus 3 squared. Yeah? So all I've done, I've just separated the variables here and checked the signs are correct. They are. Now, this looks very, very similar to a cosine function, doesn't it? Imagine that the kind of the minus 1 wasn't there. It would just be s on s squared plus 3 squared. But do you remember what we had in the first shift theorem? The first shift theorem stated that if the Laplace transform of f of t equals f of s, then the Laplace transform of e to the minus at, f of t, is going to be equal to f of s plus a. Remember we had that? And what do we have here? We have f of s plus a, don't we? Or in this case, f of s minus a. So we know that that's going to be whatever the Laplace transform of the original function was, which looks very much like a cosine function, multiplied by e to the minus at. So what we can do is that we can bring this down, and we can say that x now equals 1/10 of 1 on s minus 2, well, we know that, it's an easy one. That's going to be e to the 2t, minus, let's just write the cosine function in first, cosine at, and the a here is going to be 3. Because remember, if it was just s on s squared plus 3 squared, you say, oh yes, I know, then that's cosine 3t, because s on s squared plus 3 squared, sorry, s on s squared plus a squared is the transform of cosine at, the Laplace transform of cosine at. Yeah? So that's going to be cosine 3, but we've got a shift. Remember, f of s plus a? So that's going to be multiplied by e to the minus at, and it's not the same a, it's going to be the a that uses the shift. And it's actually going to be positive here, e to the plus 1t, e to the t. Yeah, because it's not f of s plus a, it's s minus a here. Yeah? So that should be cosine 3t e to the t plus what we have here. We've got a squared. Again, imagine that we don't have the s minus 1. Always, whenever you have something like this, just imagine that the shift isn't there to begin with. So we'll have, and if I wrote that down without the shift, it would just be 3 squared on s squared plus 3 squared. Well, we know what that is. That's the forward transform of sine at, sine 3t. So we'll write sine 3t down. But there's a shift. The s has been minus 1. So instead of f of s, it's f of s plus a. So it has to be the Laplace transform of the original function multiplied by e to the minus at. And since a here is minus 1, a here has to be minus minus 1, which is 1. So it's going to be e to the t. So tidying this up, we can say now that x equals 1/10 of, it's always good to go in ascending powers of t, but we'll just do e to the 2t minus cosine 3t e to the t plus e to the t sine 3t. And that's our final answer. And that's how easy it is to solve the second order differential equations, especially when they get a bit more complex. So hopefully later what I want to do is look at some second order non-homogenous differential equations with complex roots that yield the oscillatory motion, and just how easy they are to be solved using Laplace.